Because it was kind of soul-crushing to my first period class,
okay.
and it was unnecessary, because I don't think you're going to have that level of solution. Okay, so take a second to draw and label the forces acting on your little monkey. On the monkey as he's dangling between these two ropes. Well, force is always going to be there, just in most.
What's the question again?
Force is acting on the monkey as he hangs there. Yeah, sure. Gravity's going to act on it. Okay. How much gravity is acting on this monkey?
50 newtons.
50 newtons. How do we know that? Okay. Need to get this. If you have trouble remembering this, I would tattoo this on your hand. You're going to use it so often that you want to know that the force of gravity is mass times g, and therefore the 5 kilogram monkey would weigh 50 newtons. Okay. What other forces are acting on said monkey? Yes.
Isn't the normal force of it being held by those two vines? Isn't that considered a normal force?
The vines are providing a force, but not a normal force, right? A normal is pushing up from a surface.
Perpendicular.
What do we call the force along a rope?
A vector, you mean?
Yeah, we call it tension. Okay, so each one of those would have a tension. I'll call this one T sub B, and I call this one T sub A. Those are different sized forces. Okay. Those are the only three forces acting on the little monkey. Now, if you're asked to find the tension in those two vines, you have to apply a little bit of, a lot of concepts there. First of all, what's the net force acting on that monkey? How much net force is acting on that monkey?
How much is the tension?
He's hanging there. Not moving, not accelerating. Yeah. No net force if he's not accelerating. Right? So, we know that if we add up the forces on the monkey, there is no net force. Yeah. Okay. Just follow along. We'll be done in just a minute here. And I do have a copy up here I just discovered. Okay. So, if you look at that closer, if the net force on him is 0, then that means that if we summed up the forces in the x direction, they would equal 0. And if we summed up the forces in the y direction, they would also equal 0. Because he's not accelerating sideways, and he's not accelerating upwards, so there's no net force in either one of those directions. Okay. Well, let's look at this statement, and then look at this. What forces act in the x direction?
TA?
Yeah. There's a component of this tension and a component of this tension that are in the x direction. And I could break those down. And, this would be TB in the x direction, which would actually equal, how could I calculate TB?
Pythagorean theorem?
Really using the trig here, it's just going to be TB cosine of theta. And this is then going to be TB sine of theta. What about this guy over here? Yeah, well, this one's going to be cosine, and I'm going to call it a different angle. I'm going to call it alpha, just to differentiate. And this will be TA sine alpha. Okay, or actually we know what alpha is. We know that one's 30, one's 60, so we could have just used those numbers. Yeah.
Yeah, I was going to say, because one's 30, one's 60, the sign of alpha there would be the same as the cosine of theta.
Oh, that's
And
true.
the same with the cosine of alpha being sine of theta, so that's why they cancel.
That is true. Excellent point. All right, so look, if we take and we put these two magnitudes together, right? Let's insert these into our statement. The sum of the forces equals 0 in the x direction. Well, that means TA cosine of 30, sorry, I should have just used the numbers that I had, minus TB cosine of 60 equals 0. If you would add one of these to the other side, you'd see that this force equals this force, just in opposite directions. So think about it conceptually. That means that the horizontal component of this tension must equal the horizontal component of this tension, because those are the only two horizontal forces and they have to balance each other out. What about the vertical components? Yeah. Exactly. These two have to balance out the 50 down. Okay? So if we were to use this, and I didn't leave myself enough room, or if we use our free body diagram, we could say that TA sine of 60 degrees plus TB sine of 30 degrees. Whoops, I messed that up. This is 30, and this is 60.
Wait a minute.
Well, can't you see? Minus 50 would have to equal 0. Or in other words, these two have to add up to 50. So, right, the upward forces have to balance out the downward forces since it's in equilibrium. We're not going to take it to the end. But we're going to leave it there. You would just solve for TA or TB in this equation. Take that and plug it into this equation. Solve for the one that you have, and then plug it back in later. We're not going to do that right now. Okay. But I do have. Okay, here we go. So disgusting. Here we go. Check out these packages on this conveyor belt. You can see they're different masses. They're all multiples of m. The conveyor belt is moving at a constant speed, which is 2 meters per second, directed to the right. I want you to rank the magnitude of the net force acting on each package. Just simple ranking. Let's see, will this help?
2, 4, 3, 5.
A little bigger. Does that help? Rank them in order of net force.
Well, it gives you the velocity, the masses, the velocity and acceleration, but like velocity is going to be constant.
Yeah.
So there's no acceleration. So
Yeah.
0 times anything is going to be 0. So that force would all be 0, wouldn't it?
What do you guys think
Yeah.
about that?
Yeah.
Yeah, constant speed,
Yeah.
net force is 0. Yeah. Awesome. I'm sorry, constant velocity, net force is 0. Very nicely put. That was kind of a trick question. So if you were to rank these on the normal force acting on them, what would that look like?
It'll be like 1, 2, 3, 4.
Whatever, yeah, corresponding to the weights. That. Okay. What about the force of... No, we couldn't even do it. Yeah, what about the force of friction acting on them? Think about that for a second.
Are they like sliding on the conveyor belt, or is the conveyor belt like moving with them on it?
The conveyor belt is moving with them on it.
So like maybe it's just like and then the belt's moving, but they're not sliding.
Yeah. Yeah, Emily.
Okay, so I said that the force of friction would be They would be like the same as the normal force rankings because the equation for friction is u times the normal force. So then, if the normal force is equal to the force of gravity, it all depends on mass. So the heavier object can have a greater amount of friction than the lighter.
Is that right? Is that true? My answer to you is yes and no. Okay? Right now that they're moving at a constant velocity, how much does friction push on them? Zero. They're already in motion. Unless there's some kind of air resistance or whatever. But when they're accelerating, yes, I would definitely agree with you that they would go in the same rank. Because friction would have to push this one harder than it would have to push this one to get it to accelerate at the same rate. Okay. Good thinking, guys. All right, so...
Oh wait, is this like the practice test you were talking about?
No, the practice test is the thing you got on the way in.
Oh.
Okay, so check this out. We've got treasure chests with two forces acting on them. All the treasure chests are identical. And all the forces are identical except for the magnitudes of forces are but the directions are different. I'm going to give you 2 minutes to think hard on this one and to consider how you would rank these as far as their speed is concerned after 2 seconds. What was your ranking and why?
Oh, it's not with me.
What's that? I was just getting a near-full kind of, in a nice way, that I need to make these, print them out so you guys can see better. Somebody with a ranking, raise your hand. You think you got it? Nobody?
Like, which one?
That you have some kind of ranking, Jamie. Which one's going to have the greatest speed after 2 seconds?
D.
Okay, and then which one?
C.
Okay, and then?
A. Okay, then D.
B.
Okay.
Lucky guesses.
Let's see if those guesses are right. Yeah, okay. So that's a question we're going to have. So I want first to hear the explanation, and then Mr. Todd, you can come in and refute or whatever. Jamie, so why did you come up with this ranking?
Well, I was just looking at which of the forces cancel each other the least. So D obviously doesn't have any forces that are like in opposite directions, so it should be going fast after 2 seconds. Then C, it has forces that are canceling each other out in the horizontal direction a little bit, but it's not very much. It's the 10 on each side and it's all going in the horizontal direction. And the 16 is like only a little bit going horizontally or a little bit vertically as well.
Okay.
So that's why I read that second. B and A, like, I think what I said was right, but I'm not entirely certain. I think, that I am right. Alright. Yeah. It's 40 that way, maybe. I can't really explain why it just seemed right to me.
Okay. Lamar, did he sway you at all, or you? Oh, okay. Pretty good. That is a good ranking. Right. If you would break down the vectors that are off to the side, right, you would have a certain amount that is going up and a certain amount that is going backwards. Okay, and if we brought these in, this would be going back this much, and this would be going up this much. Right, and so you would take away from the rightward, leftward a little bit, and you'd only be left with this much to the right, and it would combine with this much upwards. And but over here, there's a whole lot more in this direction. Right, and so now your leftward and rightward forces almost cancel each other out, and you're just left with, this much force going upwards. And then these two, they totally fight against each other. So that is a really good ranking. Okay, and I think we should get on to our practice test today. Yeah.
When is the test?
I'm sorry, we do have one more. No, I'll make copies, because you guys are complaining you couldn't see it. And we'll make copies so you can see it. Okay, so the practice test is what you picked up today. And this is what we're going to do, how we're going to handle it. I'm going to give you about 5 minutes or so to work through as many as you can. And we'll talk about those after the 5 minutes. And then we'll go back to it. So you'll have some independent time, and then we'll have some group time.
You want ours monkey problems?
The monkeys you can keep.
You want to
Everybody loves monkeys, but the ones that are on the other side,